Customer Churn Prediction, a step-by-step guide. In this lesson, we will solve a real-world business problem, predicting which customers are likely to churn, leave, using the OpenML churn dataset. Customer churn costs businesses revenue, and it is important to anticipate who might leave. You will learn to load, explore, clean, and model a real dataset using key Python data science tools. The lesson covers how to understand the data, avoid common mistakes, handle errors, and apply best practices. By the end, you will be able to build your own churn prediction pipeline from start to finish. Running the cell now. Before we start using the data, let us import the main Python libraries that are commonly used for machine learning projects. Import warnings so we can control unwanted warning messages. Disable all warnings for a cleaner notebook experience. Import OpenML to load the churn dataset directly from OpenML. Import pandas for tabular data manipulation. Import NumPy for numerical operations. Import matplotlib for making plots. Import Seaborn for advanced visualizations. Import train_test_split to split our data for training and testing. Import scalars and label encoders for data pre-processing. Import random forest classifier for our churn prediction model. Import common classification metrics to evaluate model performance. Set the random C to 42 to make results reproducible. Running the cell now. Practice, try importing another machine learning library like XGBoost or LikeBM to explore advanced models later. If you are finding this lesson useful, remember to subscribe to our YouTube channel for more content like this. Understanding the churn dataset. We are using the churn dataset from OpenML ID 40701, containing 5,000 rows and 20 features. The target column is each class, which tells if the customer churned, 1, or stayed, 0. There are 16 numerical and 4 categorical features. There are no missing values in this dataset, making cleaning easier. Beginners often make mistakes such as ignoring class imbalance or not encoding categorical data. Running the cell now. We will load the churn dataset from OpenML and print a sample so you can see what it looks like. Use OpenML to fetch the dataset by its given ID. Get the pandas data frame and ignore extra outputs. Show the first 5 rows to understand the columns and values. Print those rows so you can inspect the data. Running the cell now. This output shows the first 5 rows of the churn dataset, giving a glimpse of the 20 features including both categorical, e.g., area_code, international_plan, and numerical columns, e.g., total_day_minutes, total_day_charge. Notice the mix of customer usage data and plan details, which will help us understand patterns related to churn in later analysis. Printing the head of the dataset confirms successful loading and helps us familiarize ourselves with the data structure before deeper exploration. Practice, try using the shape attribute, df.shape, to see the size of the dataset on your own. Let us inspect the data frame shape and the different data types used in the dataset. Print how many rows and columns the dataset has. Print all data types present in the columns. Running the cell now. The output confirms the dataset has 5,000 rows and 21 columns. The extra column is likely the target class. The unique data types include numerical, float 64, uint 8, and several ordered categorical types, reflecting how categorical features like phone area codes and the churn class are represented. This overview helps us understand the data's structure before proceeding with analysis or modeling. Which columns do you think are categorical, and which are numerical? Check the output above and try to categorize 2 columns. Next, let us automatically separate the categorical and numerical columns to make our analysis easier. Print all column names for a quick overview. Find columns treated as objects and label them as categorical. Find non-object columns, excluding the target, and treat them as numerical features. Print the list of categorical features identified. Print the list of numerical features identified. Running the cell now. Here, the code lists all columns and attempts to separate categorical from numerical features, but finds no categorical columns because the dataset encodes all features as numbers or strings that Pandas doesn't recognize as object-ID types. This highlights an important lesson: some categorical data might be stored as numerical or coded strings, so further inspection or conversion may be needed before modeling. Understanding column types helps us prepare the data correctly for analysis and machine learning. Categorical columns may require encoding before modeling. Try picking one and see what values it contains by using df::column.unique. Let us check the distribution of the target variable to see if the data is balanced or not. Print relative frequencies for each class label. Display relative frequency for each class. Draw a bar plot to visualize the class counts. Add a title to explain what 0 and 1 mean. Show the plot to visualize class imbalance. Running the cell now. Here, we see that about 86% of customers stayed while 14% churned, indicating an imbalanced dataset. The count plot visually reinforces this class imbalance, which is important to consider when training models, as it may bias predictions toward the majority class. Recognizing this helps us plan strategies like resampling or using appropriate evaluation metrics later on. Notice that class 0 has many more samples than class 1. What problems might this cause for training a model? If you are enjoying this lesson, please like and share our YouTube video to help others learn. Let us look at the possible categories for each categorical column. For each categorical column, print its possible values. Print those values to better understand the kinds of data we need to encode. Running the cell now. Pick one categorical column and think about how you might convert these text values into numbers for your model. Now let us encode the categorical columns using label encoding so we can use them in a machine learning model. Prepare a dictionary to store mappings between text labels and numbers. For each categorical column, create a label encoder object. Replace the categorical column with its encoded integer values. Store mapping between text and integer in a dictionary for later reference. Print the first 3 column mappings for review. Loop through the mappings to show a few examples. Show how text values were converted for 3 columns. Show how text values were converted for 3 columns. Show how text values were converted for 3 columns. Running the cell now. The output shows the label encoding mappings for the first 3 categorical columns, converting category names into numeric codes. Notice how each unique category in these features is assigned a distinct integer, enabling machine learning models to process categorical data efficiently. This step is crucial because it preserves categorical information while preparing the dataset for modeling without introducing missing values or errors. Practice. Pick a mapping and try reversing it manually on a few values in the data frame. Time to split our data into training and testing sets, making sure the class distribution stays similar in both. Drop the target column to create X containing only features. Set the target variable Y to the class column. Split into train and test sets, preserving class proportions for fairness. Print out the shape of our training set. Print out the shape of our test set. Running the cell now. This output shows the shapes of the training and testing sets after splitting the Churn dataset, confirming that 80% of the 5,000 rows, 4,000, are used for training and 20%, 1,000, for testing. Notice that all 20 features are retained in both sets, which ensures the model gets the full feature information during training and evaluation. This step is crucial for building and validating predictive models fairly. What might happen if we did not use Stratify? Test this by removing the parameter and checking value_counts on y_train and y_test. Let us scale the numerical columns so that large values do not dominate learning during modeling. Create a scalar for normalization so that all values are on a similar scale. Fit the scalar to our training set and transform numerical features. Use the same transformation on test set features. Copy the unscaled features to a new data frame for safe transformation. Copy the unscaled test set likewise. Replace the training set numerical columns with their scaled versions. Do the same transformation for the test set. Display the first row to see scaled values. Print that first row as an example. Running the cell now. This output shows the first row of the training data after applying standard scaling to the numerical features, where values are transformed to have a mean of 0 and a standard deviation of 1. Notice how the transformed values vary widely around 0, reflecting their relative standing compared to the entire dataset. This scaling step ensures the model treats each feature equally, improving training stability and performance. Why do we use the same scaler on both sets, and not fit twice? Think about data leakage and model fairness. We are ready for our first model. Let us fit a simple random forest classifier and test accuracy. Create a new random forest model with reproducibility. Train the model using the pre-processed training data. Predict churn status on the test set. Compute accuracy of the predictions. Print out the test accuracy to assess our first results. Running the cell now. This output shows the test accuracy of a random forest model trained to predict customer churn, achieving an impressive 95.6% accuracy. Notice how this high accuracy indicates the model is effectively distinguishing between customers who churn and those who stay, validating the quality and relevance of the features in the churn dataset. This step confirms our model is performing well before we move on to deeper analysis or tuning. How high would accuracy be if we always guessed the majority class? Use value_counts to check and compare. Accuracy is not enough. Let us check the confusion matrix and classification report to see if we are predicting minority class correctly. Print the confusion matrix to show errors and correct predictions. Show the confusion matrix with numbers. Print a full report including precision, recall, and F1 score. Show all the scores for both classes. Running the cell now. This output shows the model's performance in predicting customer churn on the test set. Notice the confusion matrix's shape. Most customers who stayed, class 0, are correctly identified, 850 true negatives, while the model misses some churners, 35 false negatives. The classification report highlights high precision and recall for non-churners, but slightly lower recall for churners, indicating the model is better at identifying customers who stay rather than those who leave, which is crucial for targeted retention strategies. Practice. Which metric do you think best shows how well we are finding churning customers, class 1? Why? Let us take a look at which features are most important for predicting customer churn. Get the feature importance values from the trained model. Package the importances in a pandas series with column names. Sort the importances from most to least important. Print the top 5 important features to review. Show which factors matter most for churn prediction. Plot the top 10 important scores for a better visual understanding. Display the plot. Running the cell now. Here, the output shows the top 5 most important features identified by the random forest model for predicting customer churn, with total_day_minutes and total_day_charge having the highest importance scores. This insight from feature importance helps us understand which variables the model relies on most, guiding feature selection and deeper analysis in the churn dataset. The horizontal bar plot visualizes the top 10 features, making it easier to compare their relative influence. Choose one of the top features and try plotting its distribution using Seaborn or Matplotlib. As another example, let us fit a logistic regression for comparison. Import logistic regression model from scikit-learn. Create a logistic regression object with a set random state and hire max_iter. Train the logistic regression using the scaled training data. Predict the target using the test features. Print the prediction accuracy for this simpler model. Running the cell now. This output shows that our logistic regression model achieved an accuracy of 87% on the test set, indicating it correctly predicted customer churn most of the time. Since we are working with a clean dataset containing both numerical and categorical features, this result suggests that logistic regression is a strong baseline model for this classification task. Notice how this accuracy reflects the model's ability to learn meaningful patterns from the features to distinguish churn from retained customers. Compare this logistic regression to the random forest. Does it do better or worse? Why do you think that is? Let us bring in cross-validation to estimate model performance more robustly. Import k-fold cross-validation scoring from scikit-learn. Compute scores using random forest across 5 folds of the training data. Print the average score across folds for a more stable estimate. Running the cell now. This output shows the average cross-validation score of the random forest model on the training data, indicating it correctly predicts customer churn about 95.25% of the time. This high score demonstrates the model's strong performance and reliability when evaluated across multiple data splits, reinforcing our confidence in its ability to generalize well on this churn dataset. Is cross-validation average higher or lower than the test accuracy? Try changing the number of folds and observing what happens. With imbalanced data, models can be biased. Let us compute class weights to handle imbalance for advanced modeling. Import a function to compute class weights for balancing. Calculate weights so that rare classes get higher importance. Print the computed weights for each class. Running the cell now. This output shows the computed class weights for handling the imbalance in the churn dataset's target classes, where a 0 means a customer stayed and a 1 means they churned. Notice that the weight for class 1, churn, is much higher, indicating it's the minority class and will be given more importance during model training to improve fairness. This step helps the model better learn from the smaller churn group, addressing the imbalance in the data. Practice. Try training a random forest using class_weight equals balanced and see if it improves minority class metrics. Let us break things on purpose, add massive noise to features and see the impact on accuracy, catching any errors. Create random noise of the same shape as data. Add a huge amount of noise to the training set for demo purposes. Use a try block in case we trigger an error. Create a new classifier for this experiment. Fit the noisy, incorrect data to the classifier. Predict on the original scaled features. Print the accuracy to show model performance degraded. Catches any error that might occur with a message. Report any errors that happen, if any. Running the cell now. Here, despite adding massive random noise to the training features, the model still achieves about 86% accuracy, which suggests some resilience of the random forest to irrelevant features. This highlights an important lesson: even with noisy or junk data, these models can leverage strong signals in the dataset to maintain reasonable performance. However, always be cautious, high accuracy here may not reflect robust, explainable learning. Try changing the noise multiplier. Does it always reduce accuracy? What does this show about data quality? Now let us intentionally pass the wrong data type for a parameter and handle the resulting error. Start a try block so we can catch misuse. Attempt to create a random forest with an invalid string value. Try fitting the broken classifier on our data. Catches the specific error and prints a message. Show the error to the user rather than crashing. Running the cell now. This error message highlights the importance of using correct parameter types when configuring models. In this case, n_estimators must be an integer specifying the number of trees in the forest. It reminds us that even before training, parameter validation is crucial to avoid runtime errors, reinforcing the need to carefully check inputs when setting up the random forest classifier for churn prediction. Practice. What other common mistakes can you make? Try switching 2 data frame columns or passing a negative n_estimators value. Best practices. Always inspect data types and distributions before modeling. Use train test splits with Stratify for classification problems, especially with imbalanced targets. Scale numerical features and encode categorical ones before training powerful models. Use more than accuracy to evaluate model quality, especially with imbalanced data. Always check feature importances and whether certain features dominate predictions. Compare multiple models and use cross-validation to avoid overfitting. Handle errors gracefully with try-except blocks. Running the cell now. Here is a compact pipeline: clean sample, encode, train, and predict on just 1,000 rows for demonstration. Comment explaining this cell is an end-to-end pipeline. Set the random seed so results are reproducible. Take a random sample of 1,000 rows for faster testing. Identify integer columns for label encoding. Identify numerical features by exclusion. Start a loop to label encode each integer categorical column. Create the label encoder instance. Encode the integer categorical column with the label encoder. Drop target column to form features X. Extract target as Y. Split into train and test, keeping class distribution balanced. Initialize the standard scalar and fit it on training numerical data. Apply the train scalar to the test numerical features. Create a random forest classifier with a fixed random state. Train the random forest model on the training data. Make predictions on the test set. Print the accuracy of the model on the test data. Running the cell now. This output shows the accuracy of a random forest model trained on a carefully prepared small dataset, achieving about 92.8% accuracy. Notice how the code follows best practices. It encodes categorical variables, scales numerical features, and uses a stratified train test split to maintain class balance. This highlights the importance of pre-processing and proper splitting to build reliable models, especially when dealing with imbalanced classes. Try adjusting the sample size and see how accuracy changes. End-to-end mini pipelines are great for trying out ideas. Do not forget to subscribe to our YouTube channel for more step-by-step machine learning lessons. Recap: today you covered data loading, cleaning, feature engineering, modeling, error handling, and best practices using a real Churn dataset.